1 second. Okay. Perfect. There to begin. Waiting for mail. Okay. Great. Okay. So I think we're ready to begin. So thank you everybody to come today for the SPICE-SPIN+X seminar workshop. Seminars, sorry, that I organized here myself with Libor Schmechel, Angela Wittmann, and Karen Eberster-Sitten in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center led by Martina Schliemann and Burger Hillebrand in Kaiserslautern and Matthias Klo in Mainz. Unfortunately, today we have an overlap with the DPG, so some of the German audience may not be joining us, but I hope that they will join and watch it afterwards. We do have, of course, in April again, the next week, the talk by Silvia Plicozzi, and then the further talks afterwards. So today's is Shunsuke Fukami, as well known to us. He's been here in the SPICE Center, and it is the second talk in the seminar series on a very different topic. He's professor at Tohoku University and obtained his master's from Nagoya University in 2005 and a PhD in 2012. His research is in spintronics, physics, materials, and particularly towards devices and applications to integrate them with different circuitry, but also looking at novel ways of computing, particularly neuromorphics, that type of computing. He's probably one of the youngest, most awarded people in Japan with the JSP Young Scientist Presentation Award. Young Scientist is a prize of science and technology by the MEXT, and the Asian Union of Magnetic Societies, Research Award, Protestant Research Awards of Magnetic Society of Japan, and JSAP Outstanding Paper Award. So with this, I will stop sharing and then ask you, Shunsuke, to go ahead and start your presentation, and I'll turn off here my camera and to allow you for a larger broadband.
Mm-hmm.
Thank you.
Okay, so can I start? Okay.
Yeah.
Okay, so thanks for introduction, Hairo. So I'm Shunsuke Fukami of Tohoku University, Japan. So first of all, I'd like to thank Hairo and the members of the SPICE and SPIN+X for operating this wonderful event and giving me this wonderful opportunity. So I'm really happy to have a chance to share our work with many colleagues. So the title of my today's talk is Probabilistic Spintronics and Computing and Device Physics. So today I'd like to convince you that the probabilistic spintronic device is useful for the some kind of complex computing task, and also the probabilistic phenomena in spintronic system itself is interesting in terms of physics. Okay, and these are the collaborators of this work. So, Shunkanai Hideo Ono, Spirio Datta, Keren Kamsari, and Giovanni Finocchio are the key person for the series of this work. Okay, and so before starting my talk, please allow me to give 2 advertisements. So firstly, we are organizing the second online RIC International Workshop on Spintronics, and this time we focus on the computing with Spintronics. So this event is fully online and consists of 2 sessions, live session and on-demand sessions. And in the live session will be held on April 6th, and these 6 panelists, Johan, Jinshen, Julie, Laura, Kimi, and myself will give a short talk on their chosen topic and have a discussion or a chat on each topic. And so this is just a 1.5 hour event, but in the on-demand site, the in-depth presentation given by the young, excellent researchers who were assigned by these panelists are available. So, and this event is free of charge, but registration is required. But the registration takes just 1 minute. So I hope your active participation. And as of today, all the on-demand contents are already available. So those who registers can access these on-demand contents. So I hope you will enjoy these excellent, very interesting contents. Okay, and the second announcement is about the Intermag. So according to Professor Tsufumi Hirohata and Professor Koki Takanashi, most of the presenters will give their presentation in person, and also more than 1,000 of the attendees will physically come to Sendai. So if you have not decided whether you will come Sendai, please consider the please actively consider the in-person attendance. So we are really looking forward to seeing you in Sendai. And by the way, the advance rate will be effective until April 14th. So this is just an information. Okay, so with that, let me move to the main topic. So firstly, I'd like to define the basic question of today's topic. So this graph shows the number of the published paper that includes the probabilistic and computing in the title or abstract. So you can see that the number of the papers increases almost linearly with year. And I didn't have a thorough look at these papers, but by skimming them, I found that most of them are studies of software. So this means that demand for the probabilistic algorithm increases year by year. So today I'd like to discuss that what happens if we have a probabilistic computing hardware. So I mean that now people running this probabilistic algorithm on the deterministic CMOS-based hardware. But so the situation may change if you can use a probabilistic computing hardware. So that's a question I would like to discuss today. So this is the outline of today's talk. So first, so after the brief introduction on the spintronic probabilistic computers, so my talk mainly consists of two parts. So firstly, I will discuss on the computing aspect. So I will show three kinds of the proof of concept of the probabilistic computing. So on combinatorial optimization, machine learning, and quantum simulations. And after that, I switch the gear and discuss on the device physics on these topics, so nanosecond random telegraph noise, external field robustness, and switching exponents. And after that, I will give an outlook and I will compare the case to run the probabilistic algorithm on the probabilistic hardware and the case to run the probabilistic algorithm on deterministic computers. And finally, I will summarize my talk. Okay, so let me start from the introductions. And I guess most of the attendees to this event knows well about the magnetic tunnel junction, but let me start from a few words about MTJs. So as most of you well knows, in MTJ, you can control the magnetization direction by applying the current, and also you can detect the direction of the magnetization by the resistance of the tunneling current. And this MTJ can serve as a memory element and has various functionalities, such as the non-volatile memory functionalities and high operation capability, high endurance, scalability, low voltage operation capability, and compatibility with the back-end blind process. And with these features, the people are intensively develop STT-MRAMs, and so this STT-MRAM technologies has hit the market since around 2018 with the scale of megabit to gigabit. So what I'd like to mention here is that the non-volatile MTJ technologies are fully matured, so the manufacturing technologies is now at the level of the megabit to gigabit scale. Okay, So these properties are used for the magnet-resistive random access memories, and also it is useful for the AI chip. But today I'd like to discuss that in addition to these already explored properties, there are many unexplored functionalities in spintronic systems, which include analog memory functionalities or analog digital tunability, short-term memory functionality, nonlinearity, and stochastics. So the message of today's talk is that by utilizing these unexplored functionalities, we have a chance to open the new paradigm of the unconventional computing, which is useful for the computationally hard problems. Okay, so next, let me make a few words about the computationally hard problems. So the famous example of the computationally hard problem is a combinatorial optimizations, such like the traveling salesman problems. And this is the map of the Tohoku regions, and the Sendai City and Tohoku universities are located at around here. And the Tohoku regions has many beautiful sightseeing spots as shown here. And the traveling salesman problem is to find the shortest route to go around these spots and return to the origin. And this is a very tough problem for today's deterministic computer. So the human being can reasonably easily solve this problem, but it is difficult for today's deterministic computers. And another example is a machine learning. So this is a cartoon of the spin glass in which the direction of the spin in each side are frozen to satisfy the interaction between each spins. And the machine learning is a task to find the interaction between each spin. So if we know the quantum mechanics and if we know the materials and distance between each spins, we can calculate the interaction between each spin. But if we do not know the materials and quantum mechanics, it's a very tough problem to find the weight matrix Jij that satisfies the given spin structures. And another computationally hard problems, which is not shown here, is simulation of the quantum phenomena. So that's also a very difficult problem for today's computers, but it is useful for example, the development of the drug. Okay, and for such kind of computationally hard problems that exist in nature, Richard Feynman gave a very famous lecture in 2018 in MIT entitled Simulating Physics with Computers. And in this lecture, he mentioned that if you want to make a simulation of nature, you'd better make it quantum mechanical. So this triggered today's very extensive effort to realize the quantum computers. And in the same lecture, he also mentioned, so he also gave another suggestions, and he said that the other way to simulate a probabilistic nature is by a computer, which itself is probabilistic. So this suggests another, so a similar but different computing scheme, so-called probabilistic computing. So today I'd like to discuss on the probabilistic computing, which uses a computer which itself is probabilistic. So this is very different from the quantum computers and also very different from the classical computers. Okay, so with that introduction, let me now enter the first main part, so computing, and I'd like to show you a proof of concept of the combinatorial optimization using a spintronic probabilistic computers. Okay, so the basic principle of the probabilistic computing is very simple. So it is a Boltzmann distribution shown here. So this equation, so the nature, solve a complex problem based on these Boltzmann distributions, as you know. So, and this equation tells you that the lowest energy state is most frequently observed. So this is the basic principle of the probabilistic computing. And by the way, this equation also tells you that the lowest energy state is observed by decreasing the temperature. And this is a basic principle for the quantum or simulated annealing. Okay, so let me elaborate. So this shows the procedure for the combinatorial optimizations. So to solve a combinatorial optimization problems, so first you have some problems, then you need to define an energy or cost function for the given problems. And then you map the cost function to a physical system with probabilistic nature, or in other words, map the cost function to a probabilistic circuit with a probabilistic bits. And after that, what you need to do is just watch the system and acquire the statistics. And finally, you will obtain the answer as the most frequent state. Okay, so let me explain schematically. So for the case of the quantum or simulated annealing, so first you need to define the energy for the given problems, and then you decrease the temperature gradually. And finally, you will obtain the answer as the converged state, because the converged state should be the state for the lowest energies. So this is the procedure for the quantum or simulated annealing. And for the probabilistic computing, defining the cost function is the same with this quantum or simulated annealing, but you need to keep the temperature high enough and fluctuate the systems, so like this, and take the statistics. Then, as the time goes by, we have a certain histogram. So by the highest peak, we can obtain the answer. So the highest peak should correspond to the lowest energy state, which should be the answer for the given problems. Okay, so from now on, I will show the proof of concept demonstrations of the to solve the optimization problems using the spintronic probabilistic computers. And this shows the flow of demonstrations. So to solve combinatorial optimizations, first you need to construct a stochastic or probabilistic device which has a controllable stochasticity. And after that, you need to construct a probabilistic bit or p-bit that shows a sigmoidal response with respect to the given analog input. And once you have a probabilistic bit, you need to connect the probabilistic bit and construct a probabilistic circuit in which the probabilistic bits are connected with a synaptic weight logic. And finally, you come up with a cost function. So the algorithm part. So you think about the cost function and map it to the probabilistic circuit. Okay, and in this experiment, we chose integer factorization as an illustrative example of the optimization. So the integer factorization is a problem to find the best combination x and y that whose multiplication becomes the given number. So this is a kind of the optimization problems. And as most of you knows well, the integer factorization is a very computationally hard problem for classical computers. And in fact, several years ago, the classical computers took 2.5 years to factorize large numbers. But so as you know, the quantum computers can solve the integer factorizations using Shor's algorithm. And in that case, the scalability is much better than the classical computers. And in 2001, IBM team demonstrated factorization of 15 to 3 by 5 using 7 quantum bits with nuclear spins. Okay, so now I will show step by step to solve the integer factorizations. So first, let me discuss on the stochastic device. So in this work, we constructed, we developed a stochastic magnetic tunnel junction as the stochastic device. So as I mentioned at the beginning, the magnetic tunnel junction is a core element for today's magneto-resistive random access memories. And in this memory applications, you need to set the energy barrier between 0 and 1 state high enough against the thermal fluctuation so that the stored information cannot be erased against the thermal fluctuations. And in 2001, our team discovered a very nice material systems, perpendicular easy access cobalt iron boron MgO-based magnetic tunnel junctions that meets major requirement for the practical applications. But for the probabilistic computing, you need to enhance the fluctuation between 0 and 1 state, and this can be easily realized by just reducing the energy barrier between 0 and 1 state. And this can be done by increasing the thickness of the cobalt iron boron to somewhere around 1.9 nanometers. And this shows the main measured retention time as a function of the thickness of the cobalt iron boron for different diameters from 50 to 80 nanometers. So the retention time is somewhere around milliseconds. So this is reasonably fast. So this is a very bad non-volatile memory, but useful for the probabilistic computers. And this shows the time domain MTJ resistance as a function. So time change of the magnetic tunnel junction resistance for different DC current applied to the MTJs. So that we can control the balance between 1 state and 0 state by changing the current. So this shows the required controllable stochastics. So now we have the stochastic device. So next step is construct a probabilistic bit that shows a sigmoidal response with respect to the input voltage. And this shows the unit circuit of the probabilistic bit proposed by Kerem Kamsari in 2017. And so we constructed a probabilistic bit with the stochastic magnetic tunnel junctions. And this shows the measured time averaged output voltage here as a function of the input voltage. So the time averaged output voltage shows a sigmoidal response with respect to the input voltage. So this is exactly the properties we need for the probabilistic bit. And in the time domain signal, the fluctuation between 0 and 1, so the balance between 1 state and 0 state changes with the input voltage. So at the input voltage of 1.875, we observe almost 0 state. And at the state, if we apply the input voltage of 2 volt, we have almost 1 state. So sometimes it shows a 0 state. And at the input voltage of 1.95 volt, we see an equal fluctuation between 0 and 1 state. So this is the required properties for the probabilistic bit. And this property is sometimes called stochastic neurons in the context of the stochastic neural network. And also, this shows the this is like the superposition between 0 and 1, and the probability can be changed by the input voltage. So this can be referred to as a poor man's qubit. Okay, so anyway, we have a probabilistic bit. So next step is to connect the probabilistic bit and construct a probabilistic circuit. So this is a block diagram of the probabilistic circuit. So, and this is the photograph of the constructed probabilistic circuit. So now, so we have a stochastic magnetic tunnel junction here. So 8 stochastic MTJs are implemented on this circuit. And these probabilistic bits are connected by a microcontroller, Arduino microcontrollers. So in these systems, each p-bit fluctuates continuously between 0 and 1, and the microcontroller also calculates the input returned to each p-bit depending on the state of each p-bit at each time. So what we need to do is just watching the systems and take the statistics of the p-bit states. Okay, so finally, let me explain the algorithm to solve the integer factorizations. Okay, so this is the cost function to solve the integer factorizations, and large F is the number we would like to factorize, and large X and Y are the numbers we would like to obtain. So these are the factors we would like to obtain. So once the X, Y becomes F, the cost becomes lowest. So with this cost function, we can expect that we can solve the integer factorizations. And the large X and large Y can be represented by this binary form, and small x1, x2, x3, y1, y2, y3 takes the value between 0 and 1, and so this can be represented by our constructed p-bits. So let me take an example to factorize 35 using 4 p-bits, x1, x2, y1, y2. So by inputting 35 and 4 p-bits, so here to these equations, the energy can be written like this. So at this stage, there's one important point, which is we have 3-body interaction and 4-body interactions. And this kind of the many-body interactions are very difficult to be dealt with the quantum computer, because the quantum computer uses the physical interaction between the p-bits. So, but for the probabilistic computers, we can interact each p-bit electrically, so that we can implement the many-body interactions much easier than the quantum computers. And to decrease the total energy, the input we have to give to each p-bit can be given by the derivative of the energy by the each parameters, x1, x2, y1, y2, like this. So what we need to do is just program this interaction between each p-bit to microcontrollers. And then each p-bit value changes between takes 0 or 1, but by taking the statistics, we should be able to obtain the answers for the integer factorizations. So now let me show the results. So first, we tried to factorize 35 using 4 p-bits. And so firstly, we observe the statistics before turning on the interaction between each p-bit. So at this stage, we see equal the probability from 1 by 1 to 7 by 7. But once we turn on the interactions, we see the highest peak for the position of 5 by 7 and 7 by 5, which are exactly the factor for the 35. And we next tried to factorize 161 and 945 using 6 p-bits and 8 p-bits. And we see the highest peak at the proper position of these numbers. So this result means that our probabilistic computer can solve the integer factorization and combinatorial optimizations using this scheme. Okay, so with that, let me switch to the machine learning. Okay. So as I mentioned, the machine learning is a task to find a rule behind these complex patterns. So it's very difficult problem for today's computers to find the weight matrix Jij that satisfy the given spin structures. But this is useful for example, image recognition or voice recognition. So the finding a rule behind a complex pattern is very useful for today's information societies. And it is used in today's information societies. And so if you trace the roots of today's machine learning, we can find these two seminal papers, which are presented by John Hopfield and Jeffrey Hinton about 40 years ago. So in 1982, Hopfield proposed a Hopfield network, and in this paper, he mentioned that, very shortly speaking, the learning mechanism of human brain is very similar to the ferromagnetic systems, and he indeed shows this equation in these papers. And on the other hand, in this paper, Jeffrey Hinton mentioned that by using the statistic mechanics, it may be possible to do the machine learning in an efficient way. But this kind of the equations doesn't match with today's deterministic computers. So today's machine learning algorithm is very different from the original proposal given by Hopfield and Hinton. But now we have the probabilistic magnetic systems. So if we use the probabilistic magnetic or spintronic systems, we may have a chance to open another story of the machine learning. So we tried to apply our spintronic probabilistic computer for the original Boltzmann machine learning, which was also originally proposed by Jeffrey Hinton about 40 years ago. So this is the block diagram of the probabilistic circuit, which I showed for a few minutes ago. So for the demonstration for the combinatorial optimization, the synaptic weights are fixed, and what we need to do is observing the statistics of the probabilistic circuit fluctuation. But for the machine learning, the final distribution is known, and the synaptic weight matrix Wij or Jij are unknown. So we need one more function that is a learning rule. And according to the original proposal of the Jeffrey Hinton, by using these equations and update the synaptic weight, and so by comparing the ideal distribution and the current distribution given by the p-bits, so by comparing these two distributions and update the synaptic weights, we can learn the complex, but we can find the rule that can realize the complex patterns. So based on this scenario, based on this principle scheme, we constructed a demonstration systems. And so according to the previous work, the weight update can be done by the RC circuit. So we implemented RC elements here in addition to the stochastic magnetic tunnel junctions. And in this experiment, we tested an ability of the spintronic probabilistic computer to learn the input-output relation for the XOR gate and full adders. So the for the XOR gate, the two inputs are given and one output should be so the XOR gate has two inputs and one output. So and for the full adder, we have 3 inputs and 2 outputs. And at the beginning of the learning, we do not see the prominent peak, but after the sufficient time passed, we observe the system converges to the certain distribution for the XOR gate and full adder. So for the XOR gate case, if the input is 0, 0, and 1, 1, the output should be 0. And if the input is 1, 0, or 0, 1, the output should be 1. So this is the truth table exactly the truth table of the XOR gate. And we tested 2 cases. So one is using ideal MTJ, and the other is using non-ideal, so bad MTJs. And for both cases, so non-ideal MTJ means that each MTJ has a very large variabilities. But for each cases, the system converges to a certain states. This shows the Karbach-Leibler divergence as a function of the time. So, and the Karbach-Leibler divergence means that the distribution, the distance between a certain distribution and the target distributions. So the small Karbach-Leibler divergence means that the system converges to the target distributions. Okay, and for both cases, the KL divergence converges to a small values with the time of around 1000 seconds. So this means that the weights for the XO and full adder are learned by the stochastic MTJs and RC circuit. So I mean, the spintronic probabilistic computer can be also useful for the machine learning. Okay, so finally, at the last of these sections, let me quickly show the quantum simulations. So as I mentioned, simulating the quantum phenomena is also a very tough problem for today's deterministic computers, but is useful for the societies. And it is, so the quantum computers are expected to be very powerful for simulating the quantum phenomena, but a long time ago, it can be also done by the classical bit using the Suzuki-Trotter decomposition. So one-dimensional transverse field Ising model is a representative problem of the quantum phenomena. And so according to this seminal work, the one-dimensional transverse field Ising model translates to a two-dimensional nearest neighbor classical Ising graph by the Suzuki-Trotter decompositions, as shown here. So the details are not important, but the quantum bit or the quantum state can be emulated by the classical bits, which takes 0 or 1. So the quantum problem can be solved by the probabilistic bit if we use a strong is expected to be solved by the probabilistic bits by using the Suzuki-Trotter decompositions. So in this experiment, we again used a stochastic magnetic tunnel junction, but this time we also used field programmable gate array, FPGAs. And in the FPGA, we can construct a probabilistic bit using the shared random number generator. But the quality of the random number is not so good for the FPGA. But by using the output of the MTJ-based p-bit, we found that the low quality random number can be changed to a high quality random numbers. Okay, and so for the transverse field Ising models, this is the output of the stochastic MTJ based p bits. So we have positive edge and negative edge. So at the timing of the positive edge, we update the state of the blue p-bits, which in the FPGAs, and in the negative edge updates the other half of the p-bit, orange p-bits. So by doing so, the stochastic MTJ arguments the shared random generator to become the true random number generators. So this is very powerful to solve the large-scale problems. Okay, and this shows the results of the transverse field Ising model using the this shows the results to solve the transverse field Ising model using the stochastic MTJ-based p-bits. So we used, we simulated 8 qubits transverse field Ising model using the 80 p-bits. So in this case, we use 10 replicas or 10 trotters for each qubits. And the details are not important, but this shows the results. So the blue shows the exact answers for the given quantum problems. And our stochastic MTJ-based P computers, probabilistic computers, shows a reasonably good agreement with the exact many-body quantum distributions. So this means that our probabilistic computer can be also useful for the quantum simulations. Okay, so now I showed 3 proof of concept demonstration of the probabilistic computing. So next I change the gear and I'd like to discuss on the device physics. Okay, so firstly, in the proof of concept demonstration, I showed the computation time is very long, which is around 1,000 seconds or 100 seconds. But it is too long for the real scale problems. So we have to reduce the computation time. And in these proof of concept experiments, we used a perpendicular easy axis stochastic MTJs whose fluctuation time scale is somewhere around millisecond. But to solve a large scale problem, we have to reduce the fluctuation time from millisecond to hopefully down to nanosecond level. So what can we do? So the fluctuation time is given by this Arrhenius law. So I think that you will think that to reduce the fluctuation time tau, it can be realized by reducing the thermal stability factor E over KBT or delta. But what we found is that by reducing the E over KBT, we can reduce the tau, but it is not sufficient. So it is not complete. And so we have to care about one more factor. Okay, so let me show the calculation results. So we performed a numerical calculation, so macro spin simulation for the perpendicular easy access MTJs and in-plane easy access MTJs. So for both cases, we set the thermal stability factor delta or E over KBT to 3.8 and 3.8. But for the perpendicular easy access MTJs, we assume uniaxial anisotropy. So the anisotropy field is 10 millitesla. So by applying the 10 millitesla to the longitude, the horizontal directions, you can turn your magnetization to the horizontal directions. So you can switch your magnetizations. And for the in-plane case, because it is not uniaxial, so we assumed 10 millitesla to rotate in the film plane and 100 millitesla to rotate to the North Pole or South Pole direction. So the not uniaxial anisotropies for the in-plane case. And we simulated the random telegraph noise for these two cases. And what we found is that even though the thermal stability factor E over KBT are the same, the fluctuation time scales are largely different. So about one order of magnitude different between these two cases. So this suggests that the tau zero are very different between these two cases. And so simply speaking, for the perpendicular easy axis case, the fluctuation time scales are not so high, but for the in-plane easy axis case, the fluctuation time scales are very different. And as a result, we observe a slow fluctuation between 0 and 1 and fast fluctuation between the 0 and 1 for the in-plane case. So, and so making long story short, the point we found is that the tau zero is proportional, inversely proportional to the gradient of the energy potential well. So for the perpendicular case, if we reduce the height of the energy, the gradient of the energy in the potential well also becomes gradual, and as a result, by decreasing the thermal stability factor, this part decreases, but this part, tau zero, increases. And as a result, there is a trade-off between the E over KBT reduction and the tau zero reductions. But for the in-plane case, because it is not uniaxial, we can reduce the thermal stability factor E over KBT by decreasing the in-plane anisotropies, but we can decrease the tau zero attempt time by increasing the perpendicular effective anisotropy field. And as a result, we can simultaneously reduce the thermal stability factor E over KBT and attempt time tau zero here. So based on this concept, we fabricated an in-plane easy access magnetic tunnel junctions with a sizable negative perpendicular anisotropy field. And this shows the observed random telegraph noise. So indeed, we observed a nanosecond level random telegraph noise between 0 and 1 state. So this is reasonably good for the real scale problems. Okay, so let me change the topic and then discuss on the external field robustness. So this shows the random telegraph noise, observed random telegraph noise, and so in the random telegraph systems, we observe the fluctuation between anti-parallel and parallel state. Maybe this is opposite, so this should be parallel and this should be anti-parallel. But it's not a big issue. So the averaged fluctuation time is given by the geometrical average of the tau p and tau AP. So, and if you apply the external field, what we observed is as shown here. So probably either of them are parallel and either of them are opposite side is anti-parallel. So the parallel state increases and anti-parallel time decreases with applying the in-plane easy axis external field. And so if you apply the hard axis magnetic field, the tau p and tau, the balance between tau p and tau AP doesn't change, but the average of the fluctuation time, tau average, changes drastically with the external hard axis magnetic field. So this is actually a serious problem, but because the probabilistic computer should work in a certain range of the magnetic field, but if you apply a small magnetic field, the fluctuation properties changes with the applied magnetic field. So this is a very serious issue. And actually this problem it also holds true for the quantum computers, but the quantum community has a big money, so it can protect the quantum computer from the external field. But the probabilistic computers needs to be robust against the external field, so we have to somehow increase the robustness against the external magnetic field. And what we used is using the synthetic anti-ferromagnetic structures as shown here. So this is the conventional single free ferromagnet-based free layer structures. So this free layer fluctuates with the due to the thermal fluctuations. But so this is the new structures which adapts the synthetic anti-ferromagnetic coupling. So we have two ferromagnetic layers which are anti-parallel coupling by the RKKY interactions. And this shows the MH curves for the free layer part. So at the zero magnetic field, it is almost coupled in an anti-ferromagnetic way. And by applying the field of around 150 millitesla, your two magnetization aligns in the same directions as shown here. So we have the anti-ferromagnetic coupling. So using this SAF free layer structures, it is expected that it should be robust against the external field. So let me show the experimental results. So this shows the tau p and tau p for the single free layer structures. And by taking the ratio between tau AP to tau P, it changes. Its log of the ratio changes linearly with the external in-plane HX field. But for the sub-free layer structures, its change is much more moderate than the single free layer structure. So it's indeed 6 times lower lower sensitivity compared with the single free layer structures. So the sub-free layer is indeed promising for the robust operation against the external field. And we also tested the Y field dependence, and this shows the results of the single free layer structures. And this shows the results for the sub-free layer structures. And again, the single free layer structures shows the very sensitive change of the averaged fluctuation time with respect to the external field. But the substructure shows almost constant fluctuation time with respect to the Y magnetic field. And I also note that the residual, so there's some residual change in the fluctuation time. And what we found that this residual dependence is caused by the uncompensated moment between these two ferromagnetic layers. So by carefully tuning the magnetization of these two ferromagnetic layers, we can further enhance the robustness against the external magnetic field. Okay, so finally, let me discuss on the switching exponent. So this is somewhat different topic from the previous topics. So, so as I mentioned, the fluctuation time is given by this Arrhenius law, and the delta thermal stability factor is known to be represented in such a way. And the switching exponents NH and NI are a long-standing question in the community of the magnetics and the spintronics. And indeed, the NH was first derived to be 2 by Louis Néel, but after that, by including the higher order anisotropy terms, the theorists predict that it is smaller than 2. And it is also the case for Ni. And firstly, the Ni was derived to be 1 by these papers, so the author of these papers. But another researcher derived a different value, 2, and another researcher derived the value between 1.5 to 2.0. And important point is that the experimental access to NH and NI are very difficult, and as a result, the experimentalists have just assumed the number and analyzed their experimental results. And that was not a serious issue in the era of the deterministic computing, but actually this is a crucial problem for the time averaged property of the stochastic MTJs. So this is an inevitable issue to realize a viable probabilistic computer with a stochastic magnetic tunnel junction, because the precise mathematical representation of the delta is very highly required. So we tried to experimentally determine the NH and NI using the stochastic magnetic tunnel junctions. And today I skip everything of the experimental details and jump to the experimental results. So the details are described in these papers, and so what we found is that the NH and NIs are almost equal to 2 for one magnetic tunnel junctions, whose HK1 and HK2 are written here. But in another magnetic tunnel junctions, which has a slightly smaller HK1 effective, it changes from 2 to 1 with respect to the applied bias voltage. And so the detailed investigation revealed that the ratio of the K2 to K1 effective, so the ratio between the higher order anisotropy to the first order magnetic anisotropy changes with the voltage, and as a result, the exponent, the NH and NI changes with this bias voltage. And after that, after this obtaining this experimental results, we discussed with theorists, and our final conclusion is that this behavior can be systematically understood by implementing the concept of the bifurcation in the mathematics. So in the bifurcation theory, bifurcation theory is a bifurcation is a concept to discuss the instability of the physical systems. And for the in some case, let me start from here. So in one case in which the one state is stable, and suddenly unstable and switch to the other state. So this type of the instability is referred to as the pitchfork bifurcation. And in this case, the exponent can be mathematically derived to 2. And this is another case in which the stable point gradually changes with applying the external field. And in such local bifurcation structure is referred to as a saddle node bifurcations. And in this case, the exponent is mathematically derived to be 1.5. And so this type of the change between pitchfork and saddle node bifurcation takes place by changing the balance between the higher order anisotropy and first order anisotropies. So these experimental results can be systematically understood by using the concept of the local bifurcations. Okay, so finally, let me give a comparison with the deterministic computer. So at the beginning of my talk, I defined the basic questions, which is what happens if we have the probabilistic hardware to run the probabilistic algorithm. Okay, and this graph shows the reported power consumption and sampling throughput for the deterministic hardware. So the NVIDIA's GPU, Google's TPU, and Fujitsu's digital annealers. So these are the reported values. So and these are located around here. And so in this work, we constructed probabilistic computers using the FPGAs, and our properties, measured properties, are located around here. So already its power consumption, the probabilistic hardware's power consumption is lower than the deterministic hardware. And if we use a nanosecond fluctuating stochastic MTJs and fabricate megabit arrays using today's matured STT-MRAM's integration technologies, the expected properties are located here. So the answer to this question is that we can achieve, so in principle, we can achieve a much higher performance and much lower power operations than the deterministic hardware. Okay, so let me summarize my talk. So at the beginning of my talk, so the probabilistic computing is promising for computationally hard problems without utilizing the quantum mechanics. And stochastic MTJ is suitable for the probabilistic computers. And I showed 3 proof of concept demonstrations on combinatorial optimization, Boltzmann machine learning, and quantum simulation by Suzuki Trotter decompositions. And after that, I discussed device physics, and I showed a random telegraph, nanosecond random telegraph noise can be realized by in-plane MTJs, and high external field robustness can be realized by SAF-free layers, and switching exponent can be also determined by using the stochastic MTJs. And by using the nanosecond stochastic MTJs and today's MRAM's integration technologies, we can in principle realize a very efficient hardware to run a probabilistic algorithm. Okay, so with that, let me conclude my talk. So thank you for your attention.
Thank you very much, Shunsuke. That's very exciting overall view of all this probabilistic computation that is really taking over actually and competing, I guess, with quantum computing. So maybe it's probabilistic supremacy coming up. Yeah, this is actually what I like to see as well. Some of these aspects. But before I take over maybe the questions, please raise your hand. Whoever would like to maybe ask a direct question to Shunsuke, and I'll promote you. The ones that are already promoted, like Matthias, can go ahead. You can go ahead and ask the question.
Okay.
Matthias.
Hey Shunsuke, great to hear from you. It was really exciting results. Something that I never thought about, but that you mentioned, is a question of robustness of probabilistic computing. It's very important, but in my papers, I don't care, but I think I should care. So what type of inertness against stray fields is necessary for application? How much stray field do you think we have to be able to live with and still operate reliably?
Okay. Actually, that depends on how much cost we invest. But so assuming that we can use a reasonable magnetic shielding, field shielding, I think that the 5 millitesla is a number we have to, so the magnetic field. So if we can realize the MTJ that is robust against the 5 millitesla magnetic field, it is reasonably good.
Okay, so anything that cannot operate in plus minus 5 millitesla, forget.
So yes, so I do not fully. So I'm not familiar with the shield technologies, but by looking at some papers of the shield technologies, the 5 millitesla is a reasonable value. So
Very good. Any further questions from the audience? Maybe I was not. I have a question regarding the comparison to direct computing. So at what point? I mean, it seems that in the last diagram that you were showing, that the different computation of the spin plot, the sampling in here in the probabilistic, it wasn't sure if it was directly connected to how fast the computation will be on the problem. And at some point, the probabilistic computing is probabilistic, is actually sampling. So where is the sweet spot where it can take over in terms of functionality versus deterministic kind of computing for simple tasks? Is there a rule of thumb? I mean, you can see here that for fast operations, you can take over with some of the systems by paying more power, or is it always going to win?
So yeah. Maybe so. I think that you mentioned that even though the MTJ is so fast, we need a we need a CMOS based circuit. So the higher speed is not important. So it is correct, but the point is that no relation between the timing of the update for each pivot is important. So each pivot randomly update compared with another pivot. So that's important. Okay. So yeah, you are correct. So maybe such kind of the sampling throughput is not necessary. But the point is that by so this kind of the fast sampling throughputs lead to a higher computation performance. But that's an open question. But the no relation between the timing of the update is very important.
No, my question was more into what do you mean by like computational performance? At the end of the day, what is tackling these ones are the hard problems, whereas the simpler problems, is it something that you would want to spend architecture to solve these problems because they're still stochastic, and versus some of them that are just more computationally direct. Is there a rule that architecturally, when you're designing the circuitries, would it be arguing that should we just make a fully probabilistic computer, or in combination with deterministic and probabilistic computing too, depending on the task involved?
Yes, I think so. So we should choose an appropriate scheme, an appropriate algorithm, an appropriate architecture to solve the given problems.
Okay, so it's more problem directed.
Yes.
Architecture that one will solve.
Exactly.
In those cases. Okay, very good. Any further questions from the audience? I think today was a little bit, we have 70 people in there, but maybe the most active ones that usually ask questions. Okay, hang on. We have a few. Let me promote. Yonko is here. And Yonko, we'll promote him to ask a question. Let's see if he joined. Okay, I'm assuming he joined it. Yeah, Yonko will join us. I'll be able to ask the questions directly. So Yonko, go ahead and ask your question, please. If you can unmute yourself.
Yes, thank you. Somehow the system first crashes and then lets me ask questions. Thank you for this great talk. I'm sorry that I'm in the background too.
Yeah, it's okay.
You're bigger than usual.
I didn't try to double down on myself, but
which is you.
Here a question coming from a theorist. Okay, that's very amazing what you're doing. A fleeting remark I'll make is, of course, you're not here questioning the interpretations of probability theory, but it's obvious that actually the whole idea here is based on the what I think is known as the frequentistic interpretation of probability, the frequency of occurrence of something, right? Because that's what you actually showed at the beginning, but that's a fleeting remark. My other remark is you used the terminology very carefully, I would say, when you said optimal factorization. And it seemed that you're looking for, in some sense, optimal factoring into two factors. But again, it's not clear to me if they need to be prime, because not all numbers, very few numbers actually can be factored in just two prime numbers. That's one thing. And the other thing is, I was thinking when you showed us the cost function that it was obviously for optimal using two numbers, factorization two numbers. The f being equal to xy minus okay, you can show, xy minus f. So the point is, first, it's a fun question, the one. So what if your f is a prime number? Would you get an answer that,
okay,
would you get 1 times f as an answer?
Yes. So that should be the answer the probabilistic computer should give.
Okay, and of course, related to this, there are two very demanding problems: factorization of large numbers into prime numbers, right? Do you have any thoughts about the application of the stochastic computing to this? I guess I'll stop here. Thank you.
Okay. Thanks for your comments. So I will care about it.
Wait, this young Ikao, can you please ask your question?
Yes. Can you hear me?
Yeah.
Yes.
Okay. Yeah, I have two questions. One is it always the case that the correct answer will be the most probable in the probabilistic circuits? I mean, if in some cases the energy landscape could be very strange or complicated, it's always the case that the most probable output is the correct answer. That's the one question. The other question is that the how much overhead computing, I mean, after the probabilistic computing is done, you have to sample all the results, right? Then you have to do statistics to calculate which one is the best and how much overhead do you have?
Okay.
That's my two questions.
Actually, both questions are tough, and yes. So as for the first question, I believe that the probabilistic computer should tell us the answers as the highest peak, but we have to examine it in futures using more larger circuit. But according to the theory, the probabilistic computer should tell us the answer as the highest peak. That's the answer to the first question. A second question is about the overlap. So after the obtaining the after the operation of the probabilistic operations, we need some time to analyze the results. That's also important questions. So that's also what we need to address, what we need to examine in future. But I also optimistically believe that this process is the most important. So that sampling process is the most important. So reducing the power for the sampling process should be beneficial for the total computing task. So that's the answer to the second question. And I hope that I could at least partially answer to your question.
Thank you.
Mm-hmm.
Thank you. Igor, go ahead and ask your question, please.
Okay, thank you. Previous answer to one of my questions. Another question is, should I understand that actually you built hardware for fuzzy logics?
What logic?
Fuzzy logics. This logics is developed actually field, and it is based not on the probability 1 and 0, but the intermediate.
Mm-hmm.
And another question, actually more important for me at least, that if you think about simulation of quantum problems, then what are your plans? And first of all, it's interesting for the system where Hamiltonian 0 and non-zero do not commute, and therefore Trotter decomposition requires also be made in time scale also. This is one more dimension. And what are the hopes in this direction?
Okay, so regarding the first, so your first question is that if I understand correctly, the stochastic MTJs takes the intermediate number between 0 and 1, and the inference of such an intermediate state. So is this correct?
Well, actually, it's connected more with this Gibbs weight.
Weight.
Yes, yes.
Weight means
Right. So you are using for determine the state Gibbs weights type of
Yes, the weight is analog, so the arbitrary number can be taken, and so input can be calculated based on the so for the case to factorize 35, the interaction between each p-bit can be given by these equations.
Okay. Okay, I think that we have to discuss it separately.
Okay.
To keep the audience. Second question is more important.
Okay.
Quantum, so the Trotter-Suzuki decomposition. So this.
You're welcome to contact him afterwards, of course.
So sorry. So could you repeat the second question?
Well, for Ising model, you can take a zero Hamiltonian just magnetic field, Zeeman term, and the interaction is a term of interaction. And it's easy problem in that respect that these two Hamiltonians commute. And therefore, you have throttle decomposition, very simple. In the case when you have, for example, Heisenberg model, then transversal path does not commute with this Ising path. And then you need time. And this means another direction for throttle decomposition.
Okay, that's also a tough question. And actually, so what I'd like to mention here is just that the qubit can be emulated by p-bit by the throttleization, so the Suzuki-Trotter decompositions. But so the and we tested the one-dimensional transverse field Ising model, but so. And actually, I'm not familiar with such this field, but so maybe we have to think seriously think about the advanced quantum problems. So thanks for your suggestions. We would like to try to address this such kind of the problems.
Okay, thank you very much.
Great. So I think that was great. Let me stop the streaming here now. And